Let's go ahead and we'll do this one.
Okay.
So this is a differential equation, and this is one of the things that keeps coming up about the Euler number, and the exponential function that involves the Euler number is the way they tend to solve these differential equations. So you can see that the second derivative of something often indicates you're dealing with an acceleration, and the first derivative is a velocity, and then that last number represents its position. For example, if you were doing something with physics. So these get to be really they're actually kind of super important because they solve a lot of problems that are related to position and acceleration. So, you know what this means, right?
Yeah.
Second derivative. And this one means first derivative. So really what we need to do, if this is our function up here, y equals capital A times e to the exponent kt, we need to take the derivative. And of course it's pretty easy because it's a times e to the kt, because it's the exponential function. And then we just have to do the chain rule on the kt part. So it's times k. And then the second derivative is a times, well, let's go e to the kt times k, which was the first derivative. And then we have to do the chain rule again because t is being multiplied by k, so it's a function of t. So we have to do k again. So that's really pretty easy. ak times e to the kt is the first derivative. If we simplify it, and ak squared times e to the kt is the second derivative. Does that make sense so far?
Yeah.
Okay. So this is like question number 10. This is like second year calculus in university. So, second derivative, ak squared times e to the kt plus 2 times the first derivative and then minus 3 times y. But y is just a times e to the kt is equal to 0. It's a thing of beauty so far, kind of. So what's the what tradition do we follow in math and in calculus when we get something like this?
Factor.
You are a steely-eyed missile person. Even before I wrote factor on there, you knew right away. So,
Yeah.
yeah, that's pretty good. So we have common factor of A. And
A.
yeah, A. We're Canadian. And there's an e to the kt in every one of those expressions. And then we're left with a k squared plus 2k squared minus, oh, hey, we got some company. Hey, Luke.
Hey, how's it going? Sorry for that.
Hey, no problem at all. Glad you could make it. Megan and I are just, we're going over question number 10 from derivatives of exponential functions from a couple of days ago.
Okay.
And so you were given this relationship that was basically just an exponential function. Y equals a times e to the exponent kt. And you're told the second derivative plus 2 times the first derivative minus 3 times the function itself is equal to 0. And so all we've done is we've gone through the setup and we've taken the first derivative so that we can substitute it in there. We've taken the second derivative so that we can substitute it into there. And we made the substitution, and Megan correctly guessed that you factor everything, just like always. And we're left with this relationship right here. And so we're going to look for values of A and K that make this true. So I'm only partway through my factoring. Figured this part out? Oh. So we're all the way down here. Meg, can you tell me one value of K that makes this thing true?
Being negative 3 over 8 and KT.
So when K is equal to negative 3, makes it.
Oh, yeah, you just know that, sorry.
Yeah.
1.
And when K is equal to 1, and it actually asks for values of A that will make it 0 as well. So
0.
yeah. I was expecting to trip you up on that one because it's not a binomial factor. How are you doing,
Yeah,
Luke?
you can erase that sign and just copy down after your part.
All right.
Thanks.
What did we learn yesterday? We did the we did the derivative of the natural log function yesterday. Oh, look, it's only my disembodied shoulder. We'll let Luke catch up, and then we'll do a little bit of debrief on the natural log. Did you get a chance to look at any of the natural log stuff, Luke?
No, I'm a little behind because I'm studying for chemistry, so.
Oh, okay.
But.
Well, we took the derivative of we learned what the derivative of the natural log function is, and believe it or not, this is like we're almost at the end of the calculus part, and this is it's not actually on the curriculum, but that doesn't matter. We're just sticking it to the man, and B, it's really easy. Hey, Meg, watch this, Luke.
Yeah.
What's the derivative?
1 over x.
Yeah. That's pretty easy, huh? So the derivative of the log function is just the reciprocal function, and then you can do this by chain rule. So it's 1 over x squared times 2x, which actually just simplifies to 2 over x. And of course, if it's a logarithm, x always has to be greater than 0. So we don't have to worry about zeros on the bottom. Does that make sense, Luke?
Yeah.
Okay. And the other thing that we looked at yesterday was the whole idea that you can use some of the properties of logarithms, and you can actually simplify the whole the expression first. So you can rewrite this one using the exponent rule for logs. And so, using the exponent rule, Meg, do you remember what this is?
2 natural log of x.
Right. So the exponent can come down front. You might remember that from functions. And now we can actually just do, we don't have to use the chain rule anymore. We can just use the constant rule. And it becomes 2 times 1 over x, or 2 over x. So it's just the same thing, but it all works out. Okay. So Meg, did you understand the part about using the change of base formula for logs? So,
Is that the framework for today?
yeah, that's right.
Oh, okay.
Okay, so this is y equals log base 10x. And if you dig through the preamble, I actually you'll be able to write down basically what the formula is for changing bases. So we know how we can do the derivative of the natural log function, but we don't know how to do the derivative of log function to the base 10. So the big solution here is all we have to do is change the base using the change of base property of logs, and then we can just do it like normal. So, do you remember, do you know how to do this one, Megan? We're going to switch it to the natural log.
Natural log of x, natural log of 10.
That's right. So we can actually change the base so this way. So it becomes the natural log of x on top, and then it's the natural log of whatever the base of the original log function was on the bottom. So these two things are now totally equivalent expressions. And the natural log of 10 is some number, like, I don't know, 3.1 or something like that. So it's just a constant. So really, we're just doing this. We're just going to take that derivative, and we can use our constant rule because the natural log of 10 is just a number. And what's the derivative of the natural log of x? Luke?
Another 1 over x.
Exactly. There we go. That's easy. At least I think it's pretty easy. All right. Back to something that's pretty easy again. Let's take the derivative. But let's change it. Let's change the base first. So it's a nice natural log. So this is going to be the natural log of t squared minus 5t minus 4 over the natural log of 10. So the derivative is just going to be 1 over the natural log of 10 times, I need to use my chain rule now, circle of that, and then I have to do the derivative of the inside function, so I'm just going to be doing times 2t minus 5. And I don't think there are any factors top or bottom here that are going to cancel, so I can probably leave that fine, just leave it the way it is. Quite often when we're dealing with natural logs as well, we have to worry about restrictions because we can't take the log of a negative number that's outside of the domain of the log function. So we might need to do like an interval table to figure out what values of t are legitimate here. So this is this would factor out t minus 4, t minus 1 times t minus 1, and so we'd have to say that t needs to be, let's see, needs to be either less than 1 or t needs to be greater than 4. So ordinarily I would do that with an interval table, but just to keep it sort of in the domain. Okay, any questions? Does that make sense, or did I go too fast? Thumbs up? Yay!
I was confused about like the third line, but then I didn't see like you're taking the derivative. I didn't see that.
Oh,
It
okay.
makes sense now. Man.
Okay, good. Yeah, excellent. Okay, everybody ready? Because we don't know how to do the derivative of that. Okay, so the base is just some number. In this case, we've just labeled it as the variable a. We know how to take the derivative of something with the base of an Euler number, but we just don't know how to do the derivative of that. So, got a trick. Going to take the natural log of both sides. This is just a proof. You won't actually have to do this trick every time. And I'm taking the natural logs so that I can exploit the property of the exponent property of logs. So the exponent can come down in front of the log. Okay, now I'm ready to take the derivative. And we did this yesterday, Luke. It's called implicit differentiation. So what is what's the derivative of the natural log of y?
Oh, you're asking me?
I was throwing it out there to the general crowd, but yeah, see if you can get it.
1 over y, or?
Yeah, that's right so far. That's good. And then because y is a function of x, we have to treat this like as if this is a function inside of a function. So we have to use the chain rule. So we have to multiply by the derivative of the inside function. What's the derivative of y? Meg?
1.
Nope.
1.
No. Nice try. There.
Oh, yeah.
Ow.
It's y prime.
I was like, what did you say?
Yeah, that's a little tricky. Sorry. Okay, and then we do the derivative of this side. A is a number, so this is really just a constant. So we're just going to use our constant rule. X is x to the exponent 1. So this is actually just the natural log of a. So now we just have to isolate y prime. But y is equal to a to the exponent x, and so y prime is equal to a to the exponent x times the natural log of the base. So let's do function of x is equal to 2 to the exponent x. So this is an example of something with a doubling time. We actually have we have 4 pans of brownies in the staff room right now, and we've been taking a picture of those pans of brownies every hour. And what we're trying to see is if people take like half of the brownies in the first hour, and then they take half of those brownies in the next hour. So we're actually seeing if the brownies have a half-life or not, because people are too polite to take, the brownies as we get lower and lower quantities. So this is just an example of an exponential function with a different base. And quite often biologists use doubling times because it's convenient to know when something gets to be twice as large. Okay, so this is probably easier than you're thinking. And hey, Luke, do you want to try it?
Sure. Write it down.
Is it good, or we can actually just use this as a formula?
What's that?
We can actually just,
Oh.
yeah,
Oh.
we actually don't have to go through this stuff. This is just basically our formula right there.
Okay. Yeah, that's just a proof, right?
Yeah, that's just a demonstration of how you develop the formula. Yep.
Okay. So,
Does it seem hard?
no, this is just 2 to the power of x times limit, or times base log or that 2.
Natural log of 2. Yeah, that's right.
2.
That's it. Yeah, the natural log of the base. Okay. Let's just do one more. So we don't have to get too sophisticated with these. Technically, the derivative of the natural log isn't really on the curriculum, but
What the heck?
what the heck?
Yeah. Because it sounds like pickle, but let's do it anyway. Sometimes.
It's extra work.
It's fun.
Yeah, actually, we do have to do the derivative of exponential functions, so we might as well do the derivative of the natural log. It's not that hard.
Mm-hmm.
Okay. Hey, what rule?
Chain? No. Product rule?
Yeah, so we're going to use the product rule, and we'll have to use our derivatives of exponents. Okay. Do we do derivative of the first times the second plus the second times the derivative of the first? No, that's exactly the same thing. I just said it backwards. Okay. Derivative of 5 to the exponent x, negative.
Tan of x times the natural log of 5.
Exactly. So we did the derivative of the first times the second.
I did first time second. Okay. 5x plus 4.
Very good. And we'll do a little bit of factoring here. Common factor in both terms. Luke?
5 to the power of x.
Perfect. And x to the power of 4. That's it. So I don't think we have to. We don't have to belabor these ones. So let's just do. So let's just do questions 1 and 2. So altogether, that's just like doing 6 different derivative problems, and they're just with exponential functions with different bases and logs with different bases. And so whoops. So just in differentiating exponential functions, just do 1 and 2 there. And differentiating logarithmic functions, just do questions 1 and 2 there. There, and I'm about to stop screen sharing so that.
Oh, we can see you!
Yeah, that's right. What a treat. Okay, and I've set up. I put up an assignment, and we'll have a test next week. So it's almost going to be. It's going to be like a review because it's just going to be curve sketching. Yeah, it's just going to be curve sketching basically. Does that sound okay with you, Luke? Okay, and yeah, that's about all I've got. When do you write your chemistry test?
Thursday.
Oh, okay. And
This Thursday. So.
yeah. Oh, okay. So should be able to work it in. The assignment just covers the things that are going to be on the test on Monday.
Okay.
And yeah, seems like everybody's doing pretty good. So.
The assignment due Friday then?
Yeah, if you can get it in on Friday, that'd be the best thing. And
Okay.
I'll take a look at it. If there's anything really disastrous, I'll let you know before we have the test on Monday.
Okay.
All right. Any questions?
No, that's good.
Okay. Meg, any questions?
No.
All right. Well, tomorrow we're going to do derivative of sine and cosine function, and we already know kind of what the derivatives are. So I don't think there'll even be a preamble.
Whoa.
All right. See you tomorrow, guys.
Yeah, see you later.
Bye.